we were talking about meters. In addition to the category of meter, there's also two different types of meter. There's a true RMS reading meter, and there's an average reading meter. And if you look at your meter, somewhere on it, if it doesn't say true RMS, then that means it's not a true RMS reading meter, it's an average reading meter. And the difference is this. We talked about the sine wave, the voltage and current sine waves. Well, if you look at the RMS value, and now this is what's called a fully rectified waveform, where you take the negative half cycle and you run it through some electronics, and it inverts the negative half and makes it positive. That's how a lot of electronics works. So it converts it to these pulses instead of a sine wave. But if you look at the RMS value compared to the peak value, it's right here. But if you were to calculate the average value of this pulsing waveform, you would see that it's right here. If your meter is not a true RMS reading meter, that means it's actually reading the average value, and then it uses a multiplier to give you the answer. So in theory, an average reading meter will give you the same reading as a true RMS reading meter, because it takes this and it multiplies it by that much to give you the same reading as the RMS value. And it works just fine as long as we're dealing with pure sine waves. But in our business, a lot of times what we'll do is we plug in gear like this projector that draws current in pulses or changes the sine wave in some way. So instead of the current being a sine wave, maybe it's a current pulses or DC or something like that. And when that happens, then the relationship between the average value and the RMS value changes, it grows. So that little multiplier we had before no longer works the same. So you start getting reading errors. So this is an example of a waveform that's been put through a dimmer. And if you dim it down, this is dimmed 50%, it chops up that waveform. When it does that, the difference between the average value and the RMS value grows. And your meter doesn't know that. So it still has that little multiplier. So you start to get reading errors. And you get wrong readings. Like, for example, here's a picture of 2 meters, and they're measuring the same conductor. This one says true RMS, and it says 96 amps. This one does not say true RMS, it says 90 amps. Why? Because the current going through here is not a pure sine wave. And that causes reading errors between a true RMS reading meter and an average reading meter. This one is actually calculating the RMS value. There's a computer chip in there that samples the current periodically, like 100 times a second or something like that. And it uses those values to compute the RMS value. And then it reads it out. This one is assuming that the current is a sine wave, and it's using that little multiplier, and it's giving you a false reading. So what you should have is at least a category 3 and a true RMS reading meter. So go look at your meter and make sure that it's a true RMS reading meter. This becomes really important, when you're metering something like, every conductor has a maximum ampacity. It can only conduct so many amps before it gets too hot. And if you don't know what the real value is, then how do you know if it's conducting too much current? So you need to have accurate tools. So that's one of the tools you should have. So, it's a good idea to have, have you seen that Facebook meme? There's a picture of a giant toolbox with all these tools, and it says what you bring to the gig, and then there's another picture that shows a pair of gloves and a C-wrench, and it says what you actually need, right? Well, the truth is somewhere in between the two. So what I think is important to have, and it depends on the type of job you're on. if I'm doing a permanent installation, which I haven't done in many years, but if I were to do a permanent installation today, I would bring my full set of tools. I'd bring, crescent wrench. I'd bring box wrenches, open end wrenches. I'd bring Allen wrenches and screwdrivers and all that kind of stuff. But if I'm going, to, like, for example, the show I worked on last February, the NBA All-Star Weekend. What's important to have? There are multi-tools that are really good. What's the Tools for Stagecraft makes one that replaces a crescent wrench, and it can tighten a yoke. It can do the 3/8. Yeah, it does the 3/8 inch bolts, and it does the C clamps, and it's one tool. It does all that kind of stuff. That's good to have. A pair of rubber gloves in case I ever need to do something involving high voltage or electrical. I also bring head protection, and we have a culture in our industry. We have a culture where it wasn't up until recently. It wasn't cool to wear head protection. If you wore a hard hat, you were a dork. But that's changing now, and I'm happy it is, because anytime somebody's over your head, and that riggers are in the steel, somebody's on the catwalk, there's a potential for them to drop something on your head. Now think about this. If somebody drops a bolt or a nut 40 feet and it hits you on the head, that's bad news. You can get head injuries. So do wear a hard hat when there's people overhead. I also wear electric hazard rated shoes just in case. I also have leather gloves and cotton gloves with me. I like to wear cotton gloves when I'm loading and unloading trucks or pushing gear around. What else? I do carry a C-wrench on a lanyard, so that if I do have to go up in the catwalk, I'm not going to pull the C-wrench out of my pocket and accidentally drop it. Or if I do, it'll get, it won't fall because it's connected to me. See, what else do you guys like to bring to gigs? Oh, that's a good one. Yeah, flashlight. And now I have a Petzl headlamp and I usually wear it around my neck because it like cuts off the circulation to my brain. So I wear it around my neck. But yeah, for lots of tasks, a headlamp.
I was just going to say blade.
A blade? Sure, yeah. And again, I have a multi-tool that has a blade in it and some needle nose, that kind of stuff. So that's a good one to have too. It's funny how it's almost fashionable. People buy and use tools and stuff because everybody else is using them. And one of the fashions that I've noticed is that a lot of people like the Petzl headgear, helmets. But you have to be careful about which kind of helmet you buy, because if you're an electrician, what you want is one that's either rated E or G. So a class, do I have an eraser? Anybody? No. Okay, so you want either a category E or a category G. A category E is good for 20,000 volts. A category G is good for 2,000 volts. Now, the climbing helmets, the Petzl climbing helmets are great for riggers. They're vented, but not so good for electricians. The reason is that if there's an arc flash, it gets really hot really fast, and those holes in your head can let heat burn your scalp. So you need to make sure you have the right, and Petzl makes headgear that's rated E, and they have them that are rated G. So make sure that if you go out and get that stuff, you get the right stuff. Okay, so those are kind of the tools that I like to use. But your voltmeter is very much part of your personal protective equipment. If you have the right category of voltmeter, it's going to protect you. Same goes for an amp meter, the clamp-on meter. Although it may be less important with the clamp meter because you don't need access to live exposed conductors. With the voltmeter, you need to have exposed conductors to meter it. But with an amp meter, you just clamp the conductor like this, and there's no live exposed conductors there. However, if you are close to a panel or close to a generator, then there's always a possibility that something can malfunction and you're close to a big source of energy, and that could be a problem too. So you just always need to be prepared. We already talked about that. Now, whether you are doing a permanent installation or whether you're doing a tour or a touring show, whatever, you do need, it helps. It's very helpful to be aware of the local codes and regulations. In the United States, the base level, the one thing in common that almost all the municipalities use is the National Electrical Code. So it's written by the NFPA, and it spells out acceptable practices and how you build electrical power distribution systems. If you're doing a tour, then chances are good that you will never ever see an electrical inspector. You can go visit 300 cities in the United States on a one night show, and you may never run into an electrical inspector. You may see fire marshals. The fire marshal will come out and make sure the exit aisles are not blocked, make sure that you have no flammable drops. They'll do a flame test, and they'll look for fire hazards. But the fire marshal typically doesn't know anything about electrical and wouldn't know how to spot a code violation if he tripped over it. On the other hand, if you're doing a permanent installation in a theater, in a church, or any area where there's a performance, then the likelihood is high that you will see an electrical inspector. So it pays to understand how the NEC works. And I'll give you an example. So a friend of mine in Fort Lauderdale owns a production company, and he was doing a live show outdoors one time. And I got a panicked call from him about 3 o'clock in the afternoon his time. They were doing a sound check, and they were in Miami. The local inspector, the city inspector, had come out and was poking around watching them set up for the show. And because it was an outdoor show and they had the stage there and they had some of the lights sitting on the stage, some moving lights, and the inspector started looking for the outdoor approval on these lights because it was an outdoor show. Of course, he didn't find one because there's only one manufacturer that I know of today that builds automated moving profile spots that are outdoor rated, and that's only been recent. So the vast majority of moving lights are not built for permanent outdoor installation. Well, the inspector didn't see an approval for outdoor use, so he went and told my friend, "Sorry, but you can't use those." He's like, "What do you mean I can't use them? We do this all the time." And he said, "Well, according to code, in order to use these lights outdoors, they have to be rated for outdoor use, and they're not. So I'm going to have to shut you down." So he went over to the switch, turned it off, and he tagged it. He red tagged it, which means that it's literally got a tag on it. If you defy him and cut the tag and turn on the switch, you could actually go to jail because he has the authority of what do you call it? The
Jurisdiction.
Thank you. He is the authority having jurisdiction. He does have, but what I'm trying to say is he has authority of enforcement. Okay, he can enforce the local codes. That's his job. And so I got a phone call, a panic-stricken phone call. What do I do? What do I do? I said, relax. There's a part in the code, and it's in Article 520. Article 520 is for, if you look in your book, there's actually, Article 520 deals specifically with theaters, audience areas of motion picture and television studios, performance areas, and similar locations. So this would fall under Article 520 because they were about to have a live performance. And I would argue that if you have a church that has a praise and worship band, that's a performance, it would fall under Article 520. There's lots of scenarios that would apply to Article 520. A friend of mine in Austin is putting in a kind of museum in a planetarium. And he was having trouble with the local inspector. And I got a phone call from him, and this was regard to the Sockapex cable, you know. And so I told him to look in Article 520, but you know, in the end, that Sockapex cable is not listed, so they had to change it out. But anyway, the important point is, it helps to understand, it helps to know the code, to know where to go to figure out where things apply. Because if you look in Article 520, there's in Article 520.10, it says that you can use equipment that's not listed for outdoor use in that situation as long as you have authorized personnel guarding it while it's energized. And so I texted him the information from Article 520.10, and he took his phone over to the electrical inspector and said, "Please, Mr. Electrical Inspector, sir," because you know they have the ultimate say. They can misinterpret the code and still they can shut you down even though they're not reading it correctly. So you have to maintain a rapport with them. You have to be respectful. And so he showed it to him. The electrical inspector looked at it. He went and looked in his book and said, "Oh yeah, you're right. Okay." So he went and took off the red tag, and they had a show that night. So it does help to understand how the electrical code works. So the NEC comes out every 3 years. So the current one is 2014. The next one will be 2017. They make periodic changes and updates and all that kind of stuff. It costs $85 for the soft cover, and it does come with the PDF version. The PDF version is great because you can search it. It's searchable. So on your computer you can say, give me every instance where you say GFCI. And you type in GFCI and it'll give you bang, 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 bang. All of the listings that mention the term GFCI, and you can easily find them. So it's much better than searching through a paper copy. So that's nice to have. Now, the code book, in my view, is kind of hard to understand. So it helps to have the handbook. The handbook is a different book written by somebody else that is a kind of interpretation of the code book. So if you read the code book, it's very much legalese, and personally I have to read it over and over and over and over again before I start to catch the meaning of it. But if you go to the handbook, then you can read the handbook, and a lot of times it becomes much more clear, much more quickly. Unfortunately, the handbook doesn't have all of the code, so you really need both. So you read the code, and then you go to the handbook to figure out what it just told you. And the handbook is about $110, $120, so they're not cheap. But you know, if you're doing an installation or something along those lines, then it does pay to have it handy. In the NEC, there are 9 chapters. And the first 4 chapters, chapters 1 through 4, apply to everything and everybody across the spectrum. So whether you're building a hospital, a church, a school, an apartment building, chapters 1 through 4 deal with what you're doing installing electrical systems. And then when you get into chapter 5, that deals with special occupancies. Special occupancies like the theater, like a television studio, like a carnival, like a motion picture set. Those are all special cases, and in some instances there are exceptions to what it tells you in chapters 1 through 4, like the use of equipment outdoors that's not rated for outdoor use. So, and then Article 520 is for theaters, audience areas of motion picture and television studios, performance areas, and similar locations. Article 525 is for carnivals, circuses, fairs, and similar events. So if you're doing a street fair, if you've got a live performance out, on, wherever, that may fall under Article 525, although most of the stuff that it talks about in 525 are things like popcorn machines and that kind of stuff. And then Article 530 is for motion picture and television studios and similar locations. So in a lot of instances, if your church is broadcasting, then that could be considered to fall under Article 530. So, all three of those articles are relatively short. You can read them in an afternoon. You can probably read them twice or two or three times in one weekend. And you know, I spend a lot of time going back and rereading that stuff because unless you have a particular situation, a particular application, it doesn't seem to stick as far as I'm concerned. So I reference it often. So those are the three areas that may have exceptions to all the rest of the code stuff. So now, for portable applications, once you connect your feeder to the switch, the other end of the feeder, you're going to connect to portable power distro that looks kind of like this. If you are in a permanent installation like a church or a theater, then you probably won't have one of these things. Instead, what you'll have is the feeder cable will go through conduit or pipe, you know, electrical metallic tubing, EMT, and then it'll go to a panel. And the panel will have circuit breakers, or it could be a dimmer rack. If you've got conventional fixtures like Parkans, Fresnels, Lecos, those will be connected to a dimmer rack, and the dimmer rack is fed by the feeder cable through conduit. And the conduit will come into the top, and then the dim circuits will go out the bottom or the back off to the where the lights are, where the lights live. If you're doing a portable show, then you'll probably see something like this. Now there's an important distinction in the NEC between portable and temporary. And it's important that you understand the difference between the two because there's different codes that apply to the different situations. So for example, if I'm building an apartment complex and I come into an empty lot and I'm going to start building this building, the first thing I'm going to do is I'm going to bring power in so I can plug in my skill saws and my drills and all my electric tools. So I will bring a temporary service from a nearby pole down to a temporary meter and a temporary panel that I can tie into. And that's intended for the duration of the construction project. That's temporary. If you go into an arena to do the Rolling Stones for one night, that's not the same as temporary power for building an apartment complex. That's a portable system. And there's different rules, different codes apply to portable than apply to temporary. And some inspectors will confuse the two, and in which case it can cause a lot of trouble. So when you reference it, when you're talking to an electrical inspector, then the terminology you want to use is portable, not temporary. So in this case, if we have a portable power distro, then you're going to tie in your feeder cable. So you'll connect your feeder cable to the inputs down here, and it's very important the order in which you connect it. What do you connect first? The green ground. That's right. Because you always want your system to be grounded. You never want a piece of metal, and the chassis here is made of metal. You never want any piece of metal to be ungrounded. The reason is that if there's a fault somewhere in the system and you energize it and there's no ground, that's potentially lethal. With the ground connected, it'll trip the circuit breaker and it'll save you. So you always connect the green conductor first and then the white, the neutral. Remember, these two are tied together at the supply. So that means either at the feeder transformer or at the first panel after the feeder transformer, those two are bonded together. So you connect the neutral second, and then you connect the phase conductors. And if you are flying hoists or flying truss, and you have your pickle for the motor control, you've got your chain hoist connected to the truss. If you press the up button and the truss goes down, what do? Reverse any two phases. That means you can come to any of these three connectors and swap two of them. And now when you press the up button, the truss will go up. When you press the down button, the truss will go down. So you swap any two phases. Now, these have test ports. This is a portable power distro with test ports. Those ports are there for you to be able to meter the power before you energize your system, before you turn all the circuit breakers on. So what you'll do is you'll connect this, and then you can put your probes in those holes, and you want to meter from phase to neutral between the three phases. So phase A to neutral, B to neutral, C to neutral. And then you meter phase to phase from A to B, B to C, and C to A. And you should get 208 from phase to phase and 120 from phase to neutral. While you're at it, you should also check for continuity between the neutral and the green ground. Make sure they're bonded together. Yeah, Kevin?
Every time when you see a panel like that without neutral?
Okay, so the question is there ever a time that you will see a panel like this without a neutral? Yes, there are. There's what's called delta power, which is 3 hots and a ground, but no neutral. Now, typically, we don't run into that in our industry unless you are connecting an isolation transformer. A lot of times, the audio will be on its own separate power, so they'll bring in an audio isolation transformer, and so it's a transformer, it's a feeder transformer, it's being fed from another feeder transformer, in which case the input side of their transformer will be connected in a delta configuration, so they don't need the neutral, okay? But you do need a ground. That's a mistake that, yeah, you always need that green ground. That's a mistake that some people make. They say, well, I have a neutral, so I don't need a ground. Wrong, you do need a ground. That's really important, as we saw earlier.
I'll ask you one more question.
Yeah, sure.
Is there any time that you end up seeing single phase instead of three phase?
Okay, so the question is, are there times when you will see single phase instead of three phase? Absolutely. Yeah. So, and there's different configurations of single phase as well. Sometimes you will have 2 hots, a neutral, and a ground. So that's considered single phase, but that's what's called split phase. So what that gives you is, if you only have, say, for example, these two, from this hot to neutral, you get 120 volts. From this hot to neutral, you get 120 volts. But from here to here, you get 240 volts, not 208, you get 240. That's what's called a split phase supply. It's because they take a 240 volt output and they'll put a center tap on it. So what that means is center tap is when you have a winding on the output of the transformer, and say it has, I don't know, 100 turns. And so the voltage from this terminal to this terminal is 240 volts. If I were to solder a terminal right in the middle, right here, and I were to tap off the voltage from here to here, it would be half of 240, which is 120. So that's what's called a center tap, because the tap is in the center of that winding, and it gives you half the voltage. So that's that's what they do for your house. A lot of times you'll get, if you go outside and look at, if you have the old style feeder transformer in the alley with the wires coming to your house, there'll be 2 hots and a neutral. You get 3 wires. And the 2 hots are 240 volts phase to phase. That's for your washer and dryer. Because they're heavy machinery, if you tried to run your washer or your dryer off of 120 volts, it would be more than 20 amps, which means they would have to put in number 10 wire instead of number 12 wire, which costs more money. So instead, what they'll do is they'll give you connections for 240 volts, so now your washer and dryer connections use less than 20 amps a piece, or combined actually. So that's typically what you'll find in your house. So you meter the power before you energize things to make sure it's what you think it is. And then, once you have finished the show and you're ready to load out, the first thing you do before you start disconnecting cables is what? Kill power. Shut everything off. So you turn everything off, because imagine what would happen if you went up to pull this feeder cable and it's still conducting 300 amps. What's going to happen?
Zap.
Zap. It's going to arc. Exactly. So you kill power, then you disconnect it.
Really quick, I recall seeing a tech at an installation once. I believe he was trying to measure some kind of like voltage leak between the ground and the neutral.
Yeah.
So like, I didn't know what that meant.
Okay, so Gabriel's question is, at a show, he saw somebody measuring between the neutral and the ground. Okay, so if you think about the way neutral and ground is connected, let me look in your book real quick to see if I have a picture in here. I do?
The guy got shot.
Oh,
Remember?
back, yeah, but that's not the one I'm looking for. There's another, oh, I guess I don't. Okay.
See? That's the neutral.
Yeah, but that's not the one. Okay, anyway. Well, yeah, I guess that would show the picture. That would show the same thing. Let me go back to that picture real quick. Right here, right? Yeah. So, if you look at the way we connect our power, this is the white neutral conductor. This is the green ground. They're both connected at the supply. And they're connected to the grounding electrode, which is a copper rod connected to the earth. And remember, what's the voltage of the earth? Zero. So the voltage right here has to be at 0 volts. We're forcing it to be at 0 volts. So if you meter between the white and the green, what should you read?
0.
In theory, 0 volts. That's not always the case. Why? Because, well, first of all, if you meter upstream of the supply, there's current flowing through the neutral. That means there's voltage drop from here to here, because there's resistance of the copper wire. So the voltage here could be different than the voltage here. And it could be several volts. So that's one thing that you might see. Another thing is that when should current be flowing through that green wire? Sorry? Yeah, if there's a fault. If something goes wrong. Otherwise, there should never be any current in the green grounding conductor. But sometimes there is. How does that happen? Through what's called mutual inductance. If you have a green wire next to a feeder cable, and the feeder cable has, I don't know, 100, 200, 300 amps flowing through it, there's a strong magnetic field around that feeder cable. So if you run the green wire right next to it, it can induce current into the green wire, and current can start to flow. So then what happens is, because current is flowing in the green wire, there's also a voltage drop across the green wire. So if you measure between the two, sometimes you will find a voltage difference. Now that voltage difference should not be great. You know, typically you want it to be less than 2 volts. But in lots of instances, it's a bit higher than that. It can be 5 volts, it can be 7 volts. In which case, you know, that's not the ideal situation. What I would do in that instance, if I have time, what I would do is I would go around shutting things off and measure the voltage, and then turn things on one at a time. Because a lot of times, or in some instances, what you'll find is there's one piece of gear that's causing a lot of problems. And if you can isolate that piece of gear, then you can troubleshoot it and figure out what the problem is. I'll give you a perfect example. I was doing a workshop in New York City, and one of the people in the class had measured a high voltage, and I don't remember what the numbers were, but something that I would consider to be excessive between the neutral and the ground at the panel. I said, that's not right. And I said, go in, you know, like when you're not having a show, when you're not having rehearsal, shut everything off. And then put your meter at between the neutral and the ground, and then start turning things on one at a time. And until you see that voltage come back. Well, he isolated it to one piece of gear. And what he found is that somebody had connected the neutral and the ground at the piece of gear instead of at the supply. That's a no-no. Because when you connect it here, now the normal path for current goes through the hot conductor, through the device, and then it comes back through both of these conductors. That means there's always current in the grounding conductor, and there shouldn't be. So that's what the code book calls, the term just flew right out of my head, objectionable current. The NEC says that is objectionable current. That's current flowing through the grounding conductor when it's not supposed to. So he just broke that connection and everything went back to normal. So, but sometimes you have no control over that because it's induced current. It's coupled magnetically because of the proximity of the grounding conductor with a high current carrying conductor, and it just causes current to flow in it.
How's that measurement called?
What's it called?
Yeah.
So what's the measurement called? I just call it measuring the voltage between the neutral and the ground. I don't know that there's any special term for it.
Well, what kind of problems will you
What-
find on site if you reach say like 5 to 7 volts?
Here's what happens. This happens a lot in the film industry. So they have what they call honey wagons, or the trailers where the stars go and get ready, or they're resting between their takes, or they're getting ready for their shot. They're relaxing in their mobile home. Well, these honey wagons are designed to be self-contained, so they have their own portable power generator in them, like a little putt-putt generator. And so the generator is the supply, and the neutral and the ground are bonded at the panel of the honey wagon. Now they bring these onto the set when they're doing a location shoot, and now they're not using the portable power generator on the honey wagon. They've got their own base camp with portable power generators, big plants, power plants. They're feeding power to the honey wagons from their plants. Well, if they don't break the connection at the honey wagon and they go ahead and run power up to it, now they've got, it's as if there's a connection here and there's a connection there. So now they have current flowing through the green grounding conductor. So oftentimes what happens is the entire chassis of the honey wagon is energized, has a little bit of voltage on it. So what happens is when somebody's stepping onto the stairs and they've got 1 foot on the earth and 1 foot on the metal stairs, it shocks them. Or they can be standing on the ground talking and you touch the metal frame, you get shocked. So that's an example of why we don't like objectionable current. It can cause shocks.
So acceptable would be like under 2 volts? Is that?
Acceptable is generally considered under 2 volts. 2 volts or less. So what's the order of disconnecting? That's important too. What do you disconnect first on the out?
Hot to ground.
First connect all the hots, then the neutral, and then the ground. That way the thing is always grounded while you're working on it. So thanks for pointing that out. Now, if you are doing an outdoor installation and it's going to be outside for any length of time, then you probably want to protect that piece of gear with a rated enclosure. So, for example, you're lighting the outside of a building and it's going to be permanently installed. You can't just leave it out there in the weather because water will get in and water and electricity don't mix. So there are enclosures that are made, specifically for protection against the elements. Now, there's 2 different ratings. There's a NEMA rating, which is the National Electrical Manufacturers Association rating, that pertains to the United States and Canada. And then there's international ratings, or IP ratings. And the IP ratings look like this. It's a 2-number system. The first number tells you how well it protects against the ingress of solid particles. The second number tells you how well it protects against the ingress of water or moisture. The first number can go from 0 up to 6, and a number 1 means that there's no opening big enough for you to put your fist in. That's 50 millimeters. And then a number 2 means there's no opening big enough for you to put your finger in, so it's finger protected. A number 3, there's no opening big enough to stick a Tech screwdriver in, that's 2.5 millimeters. Number 4, there's no opening big enough to put a paper clip in, that's 1 millimeter. Number 5, it allows some dust to get in, but it doesn't interfere with the operation. And then a number 6 is completely dust tight. And then the second number that tells you how well it protects against the ingress of water or moisture can go from 0 up to a number 8. And a number 1 means that it protects against vertically falling water. Number 2 protects against water falling up to 15 degrees off axis. Number 3 protects against sprayed water up to 60 degrees off axis. Number 4 protects against water splashing from any direction. Number 5 protects against water jets from any direction. Number 6 protects against powerful water jets from any direction. And number 7 protects against temporary immersion in water. And then number 8 protects against continuous immersion in water. Now, for outdoor permanent installations, you want at least an IP65. That's the minimum rating for permanent outdoor installation. A lot of the LED lights these days have an IP65 rating. So you'll see that they are completely dust tight, and so a 65 protects against water jets from any direction. Water and moisture can get in, but it's hard for water to get into it. And then if you want it underwater, you need at least a 67, IP67, or if you want to permanently mount it underwater, it should be an IP68. Sorry, is there a question? Thought I heard somebody. Okay. Now, the NEMA ratings, these are US and Canada ratings, and they go from type 1 up to type 13. Typically what you see for outdoor, like for example, transformers and junction boxes, you'll see a type 3R. So it's outdoor, used primarily for protection against falling rain, sleet, and external ice formation. And then type 6 is for occasional temporary submersion at a limited depth. And then type 6P is for prolonged submersion at a limited depth. So those are the similar classifications to IP65, 67, and 68. Now, we started off the day talking about electrical safety, and one of the things that we said is that one of the most common causes of electrocution is faulty grounding or faulty bonding. So what is bonding as opposed to grounding? So those are similar terms that are used. A lot of times they're confused. What bonding means, bonding is a mechanical and electrical connection. And every piece of metal within proximity of an electrical system should be bonded. That means that there should be should be connected with that conductor that has a green stripe on it or has green marking on it. And so that's just in case there's a stray conductor, there's a fault, there's an energized conductor touching that piece of metal. We want a path for fault current that will trip the circuit breaker. If it's not bonded, there's no way for the fault current to trip the circuit breaker. So anytime you're setting up whether it's permanently installed, whether it is temporarily, or I should say portable, right, then all the metal should be connected together. And you can take a meter, a multimeter that has continuity. So your meter has a dial on it. One of these settings is voltage. One is for current. Don't ever use your meter with the leads on it for current, because those leads can't conduct much current. Don't use it for that purpose. Get another clamp meter for that. But then there's another setting for resistance and for continuity. And a lot of times it'll give you an audible signal when they're connected, when they're bonded. So you can put it in continuity mode. You can touch one probe to one piece of metal, the other probe to another piece of metal, and you should hear it beep. If you don't hear it beep, there's something wrong, and you need to remedy that. So a lot of times you have to, not a lot of times, but occasionally you have to take some wire and some clamps or some connectors, and you have to bond things together. So for example, if you're building a stage that's on scaffolding, you know, that all that the scaffolding should be, that's metal, should be bonded to the electrical system if you're going to feed electrical to the stage. And they make like C-clamps that connect to a green grounding conductor that connects to the portable power generator. So you just clamp it onto the scaffold leg, and now you've got a bonded stage. Or here's another example. You're setting up truss. Or, you know, in the theater it could be a pipe. But actually this applies more to truss. So, you know, you look at the truss in here, it's beautiful. It's nice and shiny. And then you take a C-clamp, you know, like the old style cast iron clamp. It's got the bolt through it, and you hook it on there and you tighten it down, and it puts a dent, it puts a scratch on that truss. So what do people do? They'll take a PVC sleeve, they'll put the PVC on the cord of the truss to protect it. They call it a truss protector. So that when you've got the plastic PVC, then you put the clamp on it, you tighten it down, it prevents that bolt from digging into the truss and marring it, right? But it also isolates that truss from that piece of metal. So it doesn't bond it to the electrical system. So if you do that with all your lights, then your truss is not bonded.
If you do that and you have a safety, does that connect it?
Yeah, no, a safety isn't a solid connection.
It has to be like a real solid connection.
Yeah, it has to be a solid connection. Yeah. So no, I wouldn't consider safety to be bonded to it. So, so the point is that, you know, if you have a light with a clamp, and so you have, see if I have an example here, like this. Perfect. Thank you. All right. So here's my fixture, and here's the power cable, and this power cable connects to it right here. So I plug it in. Now notice that this power cable has a 3-prong connector. You got your hot, your neutral, and then what's the round one?
Ground.
That's the ground. So when you plug it in, that connects to that green grounding conductor that goes back to the supply. Now, if you were to look inside of this cable, you'd find 3 wires. The black, the white, the green. And then if you were to open up this fixture, pull the back off of it, and you look at the green wire, you'll find that it's bonded to the metal chassis of this light. It's connected, it's riveted, or it's screwed to the chassis of the light. The chassis is connected to this metal yoke. And if I put a clamp on it, the metal clamp is connected to the metal yoke. So when I hang the yoke on the truss and I tighten it down, now I have an electrical connection through the green conductor, through the metal chassis, through the yoke, through the clamp, to the metal truss. I've just grounded, or I've just bonded that metal truss, right? But if I use a truss protector, it's not. So if you're going to use truss protectors, just make sure the truss is bonded at some point. But if you're a better thing to do is they do make truss protectors. They're little. They're made of stainless steel. They're about that long, little rectangular pieces of steel that fit between the truss and the clamp and protect it. And because they're metal, they bond it. So now you're protecting the truss and you're bonding it at the same time. And every single fixture that you hang on it and plug in, you're bonding it again and again, over and over and over again, which makes it that much more safe. So, you know, it's just something to be aware of. So bonding and grounding is very important. And of course, you want to inspect all of your cables. Make sure nobody's cut off the grounding terminal. Make sure the cable is not broken and not compromised in any way. There's no broken wires. There's no broken insulation. I've seen this before, especially in outdoor, like amusement parks, because the sun, the UV rays, will cause the jacket to get brittle and crack. And now you've got live exposed conductors. So you want to inspect there. And you know, when something's brand new like this, chances are this is going to be good. It's once it gets put into a rental house and it's rented out over and over and over again, and it comes back, that's when you really need to be careful. What did they do to it? What abuse did it take? And is it still in good working condition? Right? So never assume. And that goes from the supply all the way to the load. You know, that means your feeder cable, your connectors, your power distro, your, you know, all of that stuff should be inspected as you're setting it all up. Now, this is part of the NEC. Tell you what, let's, we've been going for about an hour, so why don't we go ahead and take a 10-minute break.